Hello, Math Study students, and welcome to your online lesson. Today is part 2 of our video lessons on surface area. We'll be focusing specifically on cylinders, spheres, and cones as part of our overall goal to find the surface area of prisms, pyramids, cylinders, spheres, and cones. We'll know we're successful when we can efficiently solve problems involving surface area of these figures. So this slide that I've got up here is a really important one, and you may want to pause the video to write down these formulas and even make a sketch of these figures. But the three figures that we'll be focusing on in this video are cylinder, sphere, and cone, each of which have a unique formula to help us find its area. As we go through this one here, we notice that we have pi r squared, which is very familiar for a cylinder. And if you look closely, you'll notice that the base, and there's two of them, one at the top and bottom of each of these is a circle. Well, how do we find the area of a circle? It's pi r squared, and since there's two of them, that's where the 2 pi r squared comes from, which must mean that all the rest of this has to do with the sides, or that sort of wraparound part, much like a paper towel tube. A sphere, which is really just a figure kind of like a three-dimensional ball, takes our familiar formula of pi r squared, but it multiplies by 4, and that works out to be the surface area of that figure, miraculously. And then finally for a cone, which like a sphere has a base that's a circle, but there's only one of them. So we have just a single pi r squared involved in our formula, which means that all the rest of this must be that sort of pointy wraparound part that we have there for the surface area of everything that isn't the circular base. Now we'll break all these up into 3 separate examples where we can talk about each of the figures individually. So first, starting with a cylinder. What is a cylinder? Well, as I mentioned, three-dimensional object with 2 circles for bases, and they're joined together with a curved rectangle. Now, you might say rectangle. It certainly doesn't look like a rectangle, but if we break it apart, as I've done over here on the right, you'll notice that we have this circle base, which I've broken out here, and then on the bottom we have another circle base, which we've got listed here, and then we have this rectangle here, which I'm going to trace in green, which wraps around the entire length of the circles to create that, sort of paper towel tube look to it. And we already know how to find the area of circles. That's pi r squared. And since there's 2 of them, we have 2 pi r squared. Now, you'll see here that it labels the entire width of this rectangle, or its base length, if you will, as 2 pi r. Well, that should sound familiar to us because that's circumference. And circumference is, again, the length that goes around a circle. Well, since this rectangle has to wrap all the way around the circle, that must be the length of circumference, 2 pi r. But it's really acting more like a base of a rectangle, and we would still need the height over here, and that height is going to get multiplied, since we're dealing with a rectangle, times its base. Well, the base is circumference times height, and then we would add those together. So that's our formula for a cylinder. Let's do an example. So given the following cylinder, find its surface area. Once again, we're going to be dealing with 2 circles, so that's 2 pi r squared, since it's area, plus the rectangle, which we know is the circumference of the circle, 2 pi r, times the height. Now that formula looks really long to me, but you'll notice there's actually only 2 variables involved, r and h. Unfortunately, we are not given one of those variables on the labels on our picture. What we are given is the total width, if you will, of one of these circles, or of this overall cylinder. So that would be like its diameter. And to turn diameter into radius, we have to divide by 2. Since 10 divided by 2 is 5, that is our radius. So as I start to fill in this area formula, I get 2 pi times our radius, which is 5. Again, the 5 was half of our diameter, squared, plus 2 pi radius again, still 5. And now we need the height, and that's the height of the overall cylinder, also the height of the rectangle that's wrapping around it, which is 12. Now we can go ahead and simplify this. 5 squared is 25, and I'm multiplying that with the 2 here, so I get 50 pi plus 5 times 12 is 60, and I'm multiplying that 60 by 2, so I have 120 pi. And then when I combine these together, since they both have pi, I have 170 pi. Label would be inches squared because we are dealing with surface area. And you certainly could throw that into a calculator and get a rounded answer. We would round it to 3 significant figures, but I'm going to leave mine exact. Onto a cone. What is a cone? Well, a cone is another 3-dimensional figure. Like a cylinder, it has a circle for a base, but there's only one base on a cylinder. Like a pyramid, it has a sort of apex or vertex up at the top where the wraparound region is coming to a single point. And we utilize the formula that is shown here. Once again, that formula is based off the fact that there's a single circle for a base, and the area of a circle is pi r squared. And then we know that the rest of this, pi r times L, which is this slant length. So not the overall height. We don't care about that for surface area, but the actual slant length going from the base to that top point, also known as a vertex or apex of our object, is going to get multiplied by the pi r. And then we add those together, the surface area of the base along with that wraparound region. So let's try it out. Once again, let's start with our formula. So our area equals our circle base, which is pi r squared, plus pi r times our slant length. Well, this time they actually gave us the radius, which is 5 centimeters. So my area is equal to pi times 5 squared plus pi times 5 times my slant length, which was 10. So I end up with 25 pi for my first term, plus my second term, which will be 50 pi. Once again, like when we did the cylinder, both of these have pi's involved, so they're like terms. I can combine them, and that's 75 pi. Units was centimeters, so I would have centimeters squared. That's the exact answer. If we want to round that, of course, we can throw that in the calculator. We would use the pi button and not 3.14 because we don't want to round until we're at the very end, and then we could round that to 3 significant figures. For our very last example, we are dealing with a sphere, and we want to find its surface area. Again, a sphere is just like a ball. It's 3-dimensional, round in every direction. No flat regions anywhere on it. It has a radius that connects from the center of the sphere to any other point on the sphere itself, and that would be its radius. Again, it's half the measurement of the diameter. And our formula is our circle formula, which is pi r squared times 4. Why that works out, it's sort of the magic of mathematics and the magic of a sphere as far as I know. There might be some way to sort of prove this and show this, but as it turns out, that's the formula we use. So I'm going to do 4 times pi times our radius, which in this case is 2.8 centimeters. Had they given us a diameter, we have to cut it in half first, but this time they gave us our radius of 2.8. So there's only one variable involved in this entire surface area problem. Again, remember that we are finding surface area, so that would be if I wanted to paint this round ball or something along those lines, all the surface that is getting covered, the outer region. And I am going to use a calculator on this one, at least to combine the 4 and the 2.8. And I end up with 31.36. And that's not times pi yet, or I have not multiplied that times an approximate value of pi. And notice everything here is exact. I didn't round. I have 4 significant figures because I didn't round anything. And I could leave my answer that way with a label, and the label would be centimeters squared, once again. Or if it was asking me to approximate this, I could throw it in the calculator, and I end up with 98.520, whoops, 0. And I'm going to put a dot here because it goes on 3, 4, 5, 6, 2, and on and on and on. And then I could round that, since it goes on and on forever, and I'm eventually going to have to stop to 3 significant figures, which would be 98.5 is the third significant, and since there's a 2 after it, I'm rounding down to just 98.5. And again, that is centimeters squared. So a lot of times the problem will tell you if they want you to leave it exact or to round it. I'm often a fan of leaving it exact. For one, it's higher accuracy. You can always round afterwards, but if I'm just given a rounded answer, I can never go back to the exact without doing the work once again. And that, ladies and gentlemen, is surface area of spheres, cones, and cylinders. Until next time.